reflect matrices or, you know, whatever, vectors, triangles, whatever, we can reflect those things using the special reflection matrices. Now, there is a rotation matrix that will rotate. Here comes Derby. Just behind. There is a rotation matrix that will rotate whatever you want to rotate. So that matrix is this. So whatever you want to, whatever angle you want to rotate through, this is the matrix that you'll use. So problem 12A, I'm in my notes now, picking up where I left off, I think. You didn't? Well, I'm not going to do all of those. We talked about the matrices, right? So you just have to multiply. It's easy. I'm not going to talk about all those. We got it. So we've got an angle of 118 degrees. So my matrix is going to be the cosine of 118 degrees. So I'm going to make sure my calculator's in degrees. And then the cosine of 118. So negative, I'm just going to round it 100, negative 0.47. And so this will also be negative 0.47. And then the sine of 118 degrees, 0.88, and negative 0.88. So this now becomes my transformation matrix. The matrix I'm going to use to rotate my triangle ABC, which is from the previous page, negative 1, 2, 3, 0, and negative 3, negative 5. This is A, B, and C. Point A, point B, and point C. So my job is to rotate that triangle through 118 degrees. And then what comes out is going to be the new points, A prime, B prime, and C prime, the new A, B, and C. After we've taken this triangle and rotated it 118 degrees. Oh, David, when did you show up? Never mind, we're glad you're here. Okay. Now, this is a 2x2. All of your transformations are 2x2s, your reflection, your rotation, you know, all of them. So we have a 2x2, we're going to multiply it by a 2x3, and that's why I'm going to come out with another 2x3. Okay, so now we're going to multiply. And I'm going to use my calculator to help me because this arithmetic is more than I can handle at the end of the day, or ever probably. So, to get this guy, remember how this works. We take the first row times the first column. So we're going to take negative 0.47 times negative 1, and we're going to add negative 0.88 times 2. Everybody remember that? If you need to write it down, write it down. It's negative 0.47, negative 0.88 times negative 1 and 2, and add them up. So that's the arithmetic that we're doing to find that number right there. So that will be, that will be 0.47 minus 0.88 times 2. I got negative 1.29. And then I'm going to take this times this. So first times first, second times second. If you are uncomfortable with matrix multiplication, you need to get in here during office hours because we have to know how to multiply matrices. So first times first, second times second, and add them up. So it really helps when there's a 0 in there. Negative 1.41. And then these times these. So negative 0.47 times negative 3 plus -0.88 times -5. I got 5.81. Now, you know what to do, right? To fill in this bottom row, now we gotta use our bottom row. So we're gonna take this, 0.88 times -1, -0.47 times 2. And add them up. So I got -1.82. Say something if I've got the wrong number here. I don't wanna mess this up. So what that means is that the original triangle that had these coordinates, so vertex A was -1, 2, so on, those coordinates are now -1.29, -1.82, -1.41, and -2.64, and 5.81, -0.29. I wish we had more time, because what we could do now that's interesting is we could find the area of this triangle, the original triangle, and then we could find the area of this rotated, the image, what we call the image triangle. And what do you think is true of those two areas? If we found the area of each one, they'd be the same. And so would their perimeters, because when you reflect and rotate, you're not changing the size or shape, you're just changing the position, right? We don't have time to do that, but you get it, if that's what would happen. Okay, we all right with that? Now, I know I didn't do all of the reflection ones yesterday, but they're done the same way. You just use the reflection matrix instead of the rotation, okay? David?
Do you have to memorize the rotation matrix?
You do. Never changes. I mean, this is it. It never changes. But yeah, you know that. Okay, now let me do one more with that. It says find the coordinates of just a vector after it's been rotated 213 degrees. So now I need to build a new rotation matrix, 213 degrees, using this format. So cosine 213 on -0.84, and then sine 213 Everybody okay with that? And instead of doing a whole triangle, you're only doing one vector, and he has coordinates -3, 1. Now, is this multiplication possible? Well, this is a 2 by 2. What's this? 2 by 1. Not only is it possible, but look at what you're going to end up with. Of course you are, because you're taking a vector and rotating it, so you're going to get another vector, right? Absolutely. Okay, so let's see what we come up with. Multiply these times these. That's what we're doing. So first times first, second times second. And again, please double check me if I made a mistake, say something. Is that what you got? Wait, I did want to do something with this stuff. First of all, are those the right numbers? I don't want to go on if they're not. Are those numbers look okay? Okay, so what's the magnitude of this vector? The magnitude of that vector is root 10, right? The length of it, square, square, add them up, square root. All right, let's do this one. What's the magnitude of that one? 3.06 squared plus 0.78 squared. Did you get the square root of 9.972? Now, that's pretty darn close to the square root of 10. Why isn't it exactly the square root of 10? Because all that's rounded off, right? But here's something else really cool. Let's find the direction angle for that vector, okay? So the direction angle for negative 3, 1 would be this, agreed? So remember how we do that. This is negative 3, this is 1. We're going to second tangent 1/3, and then subtract that from 180. So the direction angle for the given vector, what's called the pre-image vector, was 161.565 degrees. Okay, that's old news, right? You need to remember how to do that. Now, let's do the same thing for our new vector. What is the direction angle for our new vector, which is over 3.06, like this? Well, that one's going to be easier because it's in quadrant 1, so I'll just second tangent 0.78 divided by 3.06. And I got 14.3. Now remember, this rotation was through how many degrees? 213. So let's take 161.565 and add 213 to it. I got 374.565, which is more than a revolution, so that would come down to 14.565, which isn't exactly what I got, but again, it's because of the round off. Pretty neat, right? Yes, Mrs. Ward, that is pretty darn neat. Okay, so the last thing we did on the other day was we reflected using the reflection matrices. Today, we're rotating using the rotation matrix, but the arithmetic is the same, the way you do it is the same thing. All right, now we got a couple of application problems we need to look at. So let's see if you can figure out how to do this next problem about egg production. Okay. So here we go. Happy Valley Farms produces 3 types of eggs. The number of dozens of type eggs sold at grocery store J is represented in the matrix. All right, so do you understand what that even means? A-I-J, this is row, this is column. So the rows are the I part, the J's are the column part. And what does I represent in this problem? The type of eggs. So the rows are the types of eggs. So this is large, extra large, and jumbo. That's the type of eggs that we have. It tells me that in the problem. I's are rows. So the rows represent the type of egg. Then the columns represent the grocery stores. So these are the type, the 2 stores. He's selling to 2 stores. So this is store 1, and this is store 2. So if I look at this entry right here, what does that entry tell me? I am selling 70 dozen extra large eggs to store number 2, to Kroger. Okay? All right. Now, the price per dozen we charge is this matrix. So B is 80, 85, and $1. So again, what do these represent? Types of eggs. So this is your large, extra large, and jumbo, and this is the price per dozen. So that says a dozen large eggs costs 80 cents. Now, find the product. What's this mean? What does that mean? What's that T mean? Transpose. What does it mean to transpose? Switch the rows and columns. So instead of having this matrix, I'm going to switch the rows and columns. So now my first column is 160. I'm going to make this bigger. My second column is 120, 70. And my third column is 200, 120. All right? David?
So isn't the T with the B?
Oh, it is, thank you, I'm sorry. Yes, that's A transpose. Thank you very much, David, you're exactly right. You are exactly right. So I need to lay this on its side. Thank you very much. Yeah, that's B transpose, perfect. Yes, the T is with the B. All right, so now when I switch it on its side, now the row gives me the prices and the columns give me the types of eggs. So this is large, extra large, and jumbo now on the columns. And I'm going to multiply that times matrix A, which I'm not changing. And in matrix A, we said that the columns represent the type of eggs. So this is large, extra large, and jumbo. And these were the store types. So this is store number 1 and store number 2. That hasn't changed, right? Now, can I multiply these? I sure can, because I have a 1 by 3 times a 3 by 2. So I'm going to end up with a 1 by 2. Now, okay, so let's do it, and then let's talk about what it means when we do it. So, row times column. So, 0.8 times 100 plus 0.85 times 120 plus 1 times 200. I got 382, I hope that's right. 0.8 times 60. 0.85 times 70, and 1 times 120. 227. Is that what you got? Okay. Now we got to talk about what in the world does that represent? Well, if you understand what the original matrices represent, it's easy. Because you multiply price by type times type by store. So price by store, that's exactly, these are the prices, and this is for store 1 and store 2. And when I say price, what I mean is store 1 buys $382 worth of eggs, and store 2 buys $227.50. Awesome. One more, and we're finally done with this section. Okay, here we go. Now we're building houses. Everybody good with this? Because I'm going to erase it. We okay? All right, so now we're going to build houses. And they give us a matrix. Write that one down. We're gonna need it. So this matrix is 976. Don't act like you're bored. This is exciting. All right, what's this matrix stand for? What are the rows? The rows are the type of house. And what are the columns? The material. Now, it said, okay, now, it tells me that we also have prices in there too. So we're gonna probably have to build a matrix out of that in a minute. Write a matrix product that gives the number of units of each raw material needed to build the houses. Now, this is the matrix that tells me what I need for each kind of house. So if I want to know how much I need to build my ranch houses, I'm going to have to need to know how many ranch houses there are. Does it tell me that in the problem? It does. So this guy is a 3 by 5. So I'm going to have to multiply him by the types of houses that I have. So I think I'm going to multiply him by this matrix, 6, 7, 14. Because the the row is the number of houses. And what do these columns represent? What does that 6 represent? Ranch. So this is the type of houses. So when you say, Mrs. Porter, how did you know to build it that way? I need to multiply, when I do this multiplication, this is number by type, and I want to multiply it by type. I want these match when I multiply. So I'm multiplying it by type by materials. So I'm going to end up, when I do that, with a matrix that is 1 by 5, and its rows are going to represent the number of houses, and its what do I call it? Columns is going to be the materials. So actually this is, oh wait, is that what I want to do? I'll just multiply it and see what happens. So to do this, we're going to take this times this. So that's going to be 30 plus 49 plus 84. So I got 163. Now before I get any further, I want to stop and think about, what does that mean? This is steel. Yeah, I'm good. I'm good. What that's going to represent is what? What's that 163 represent? Lane?
The total amount of materials that you're going to need.
Steel. It's the steel I need for my ranch houses. For my 6 ranch houses, this is going to be how much steel I need. And then when I do, oh no, that's total houses. That's not just ranches. That's total houses. Yeah, that's the number. Yeah, that's the total number, because this is all steel. So 6, 7, and 14. That's the total steel I need to do all of my homes. And then 6 times 22, 7 times 20, and 14 times 27. That's going to be the amount of wood I need. And 6 times 14 plus 7 times 10, 14 times 8. That's how much glass I need. this is telling me how much material I need altogether. Boy, my numbers are getting all jumbled up in my head. I hope that's right, 175. And 439. So if you're the contractor and you need to go out and buy paint, you know you need to buy this much paint to get the job done, to build all the houses in your plan. Now I bet we want to know how much it's going to cost us. Now, we gotta be careful because if we want the total cost, then could we multiply this matrix? This is how much steel I need. Could I multiply this matrix times the cost matrix? So the cost matrix, let's see, this is what I've got. So the cost matrix would have to be written this way. And it's 1,600, 900, 500, 100, and 1,000. Now, if you did this isn't going to answer question B. If you did this, you got a 1 by 5 and a 5 by 1, so you're going to end up with a single number. Does that make sense to you? What will that single number represent? The total cost of building all the houses. Okay? That isn't what the question says. That's how you could do it to answer that question. But this one says, write a matrix product that gives the cost of each house. A thought on that?
Couldn't you just do that and then divide by the number of houses that you have to get the cost per house?
Okay, you could. I think what they mean, maybe I'm not reading the problem right. I think what they mean is each ranch house, each Cape Cod house, and that would be different. The cost of each house each type of house is going to be different. So if I took this and divided, it would give me the average price. Does that seem right? And I'm not interpreting the problem that way. I could be wrong. Lane?
Could you just use, so that same cost matrix and then isolates for like the ranch house at 5, 22, 14, 7, 17 and multiply that cost matrix?
Oh, so what you're saying, Lane, is take this matrix right here.
Just using like the ranch house part of it.
Okay, I need each one, so I'm gonna use
And then do
the
it
whole
3 times.
thing. That's right. So I'm gonna take this one and multiply it by the cost matrix. And then, Lane, let's look at what we get if we do this. Okay, so forget that, I'm taking this matrix here, this original matrix, which is a 3 by 5. I'm multiplying it by a 5 by 1. So I'm gonna end up with a 3 by 1. Right? And these three numbers, this will be the cost of the ranch houses. This will be the cost of the other houses and the other houses. All right, so I know you're gonna multiply, but let's go ahead, let's do at least one of those. So I'm multiplying this row times this column, and that will be my ranches. So 5 times 1,600 plus 22 times 900, 14 times 500, 700, and 17,000. I got 52.5. Anybody else get that for that first one? And then I would do the other ones the same way, but I'm kind of over this right now. What's that 52.5 represent? How much it cost me to build a ranch house, yep. Build my ranch houses, it's gonna cost me that much to build them. Okay? Everybody understand this number, first of all, is it right? Anybody else get it? Okay, so we understand what that represents. And then this number, when you took this row times this column, that number would represent the cost to build a Cape Cod. And then this would be the last kind of colonial style. David?
How do you know that, like, before you do the problem, that the answer is gonna be a 3x1? With just
You asked me that same question the other day. So listen, here we go. When I multiply matrices, the inside dimensions have to match,
Yeah.
and the outside dimensions tell me how big my answer is. Right? That's how we multiply. You always gotta check this data, because sometimes you can't multiply. Right? And that guided, at least in part of these problems, that guided how I set up my matrices. Because when I have a single row or column of numbers, I can set it up either way, but I set it up purposefully so that I would be able to multiply them. Okay, whew, 7-2, done. Any question about that? We're all good. We understand what these numbers mean. Okay, and what this number would mean right here if we did that. Okay. Now, we're gonna talk about, that homework will be due on Friday, 7-2 will be due on Friday. We're gonna talk about, now solving systems of equations using a brand new method for you. We're gonna use Gaussian elimination. Now, Gaussian elimination is the process, it's a process of putting a matrix into what's called row echelon form. So Gaussian elimination is the process that puts a matrix into this form. So we're gonna learn the process so that we can answer or solve big systems of equations. What is row echelon form? Row echelon form says the first non-zero number in each row is a 1. And under every entry, under those leading ones, is a 0. These are the leading ones. So in other words, if your matrix is going to be in row echelon form, you can have 1, 2, 3, 4, 5 across the top, no problem with that at all. But everything under that, right there, has to be a 0. So these are all going to be zeros. And then the first number in this row that isn't another 0, so I could put a 0 here, but the first number I put in that isn't a 0 is going to have to be a 1. And then I can have 5, 7, nothing wrong with that. But every number underneath this has to be a 0. And the first number in every row that isn't a 0 has to be a 1. So what will happen is these will also be zeros. And then maybe if you're 1 and a 3 and a 0 and a 5 or something like that. Or 0 and a 1, I'm sorry. That matrix is in row echelon form. Now, typically and ideally, what it looks like is this. you want to have happen. We are going to be looking, at least initially, at systems of 3 equations, 3 unknowns. So here would be our x, our y, and our z. Here are our 3 equations. So this says 1x plus 2y plus 3z equals 4. That's our first equation. If we can get our, and then our second equation would look the same, and our third equation would look the same. But if we can get it into echelon form, what does this bottom row now say? Z equals 5. And then if we know z is 5, can we back up here and find y? And if we know y and z, then we can back up and find x. Now, in the matrix's original form, okay, I'm making this up totally, but this is, you can't look at this and solve it, right? This is an x, 2y, 3z equals 4, 2x, y, 2z equals 3. You can't solve that. But when you get those 1s and 0s in there, now it becomes easy to solve. So Gaussian elimination is the things we do, the process we do to make the matrix look like that, row echelon form. Okay? Now, reduced row echelon form takes it a step further. Reduced row echelon form adds a third criteria. And the third criteria is that every entry above the leading ones is 0. Okay, so 1 and 2 give you row echelon form. 1, 2, and 3 give you reduced row echelon form. The process of putting a matrix into reduced row echelon form is called Gauss-Jordan reduction. Now, personally, I don't feel that the work involved with going that extra step is time. I think it's easier just to do back substitution here. If I know z is 5, I'm going to plug it in, get y, plug it in, get x. If we did go the extra steps though, every entry above the ones is also 0. The matrix would look like that. Wait a minute. What's good about that? That gives you your answer. Because it literally says x equals 4, y equals 3, z equals 5. But understand, these zeros don't just happen. You have to do work to make them happen. And finding the upper zeros, we call this the upper triangular zeros, finding those doubles the amount of work. As you find these 3, then you got to turn around and find these 3. So we're going to do, I don't care, you can do whatever you want. We're going to do reduced echelon form on our calculator, because pushing that button is as easy as pushing the other button. But by hand, we will only be doing Gaussian elimination. That's all I require you to do. You can do it on your own if you wish. Okay, so let's make sure we got the vocabulary. Gaussian elimination is the process associated with putting a matrix into row echelon form. Gauss-Jordan reduction is the process associated with putting a matrix into reduced row echelon form. And then this is the definition. 1 and 2 are row echelon form. 1, 2, and 3 altogether make reduced row echelon form. Okay. Boy, how are we going to do this? Well, we're going to use what are called the elementary row operations. All right, so let's start with number 1. Here we go, guys. Come on, this is going to be fun. It's your first time. And doing it by hand is kind of a lost art, but if you take finite math at IU or IUPUI, they make you do this by hand. So we're going to at least go through it and get it figured out. Okay, so first of all, you understand my matrix I wrote here? Okay, this is called an augmented matrix. It's got the variables and the constants both all in the same matrix. This is an equation, this is an equation, this is an equation. Does it make sense to you that I could multiply any row I wanted by a number? So if I want to multiply the bottom row by 3, I could do that, right? Because essentially I'm multiplying an equation by 3. Also, there may come a time when I want to flip these two. I don't like them the way they are, so I'm going to flip them. Would that be okay? Yes, because I'm just writing these equations in a different order. That does not change anything. So when we talk about these elementary row operations, we're just talking about things that we normally do. We can multiply by a scalar. We can interchange rows and columns. We can add rows together. Well, now wait a minute. Have we ever done that? Have we ever taken these two things and added them together? Every time you do elimination, right? So everything we're going to do is stuff you've already done. We're just doing it in a matrix. All right, so here we go. I know you cannot wait to get started. There is nothing wrong with the top row, so I'm going to go ahead and just recopy it. Remember, my goal is row echelon form. So don't these guys have to both become zeros now because they're under that 1? So I'm going to do what I do when I eliminate. I'm going to take that top row and I'm going to multiply it by -3. I don't like to keep building new matrices, so I just do the work right here inside, but you'll develop a style that works for you. I'm multiplying my top row by -3, and it gave me these numbers. Now, guess what I'm going to do with my new top row, which is red, and my second row? Guess what I'm going to do with these guys? I'm going to add them. What's going to happen when I add them? Well, that's going to be a 0, which is exactly what I needed it to be. Then this is going to be a 1, which is also joyous good news. That doesn't always happen, but it happened. -2 and -7. So my new second row with the x's eliminated is that. All right. Now I gotta eliminate this guy. I gotta make him a 0. So I'm gonna go back to the top row. And I'm gonna multiply the top row by -2. So I'm taking my top row and I'm multiplying everything in it by -2. And then guess what I'm gonna do with them? I'm going to add them to the bottom row and get a new bottom row that starts with a 0. That was my goal. And then 2 and -3 and -11. You okay with that? Now, that's perfect, except I need one more 0. Where do I need my next 0? Right here, right? So, there is nothing wrong with the top 2 rows, so I'm going to just recopy them. They are fine. But I need a new bottom row. Now, don't use the top row, because what will happen if you try to use the top row, you could actually add those together and eliminate straight up, but why will that not work? Because he's going to put a 1 here, right? So I'm going to have to use my second row, because that's the only way I'll be able to add and keep the 0 right here. So I'm going to take my second row, my new second row right here, and I'm going to times it by -2. So my second row by -2, so that when I add it to my third row, I'll get a 0. Oh my gosh, I got another 1, that's awesome. And now my matrix is in row echelon form. And everything we just did is called Gaussian elimination. Okay, now your calculator does it with the press of a button. You have to take some steps. All right, so now solve the system. Remember what the columns represented, x's, y's, and z's. So what does your bottom equation say? Z equals 3. And then y minus 2z is -7. Remember, there's an equals here. So y minus 6 equals -7. Excuse me, so it looks like y equals -1. And then all the way to the top, x minus 2y plus z equals 7. So x plus 2 plus 3 equals 7, so it looks like x equals 2. So my answer is 2, comma, -1, comma, 3.
I'm really confused how you got,
Yeah.
you got 4. Oh, you,
Yeah, multiplying this row
oh.
was -2 times -2. Yeah, no, I don't multiply the row that I'm finding zeros in. I want you to understand what just happened here, what you just did. These equations that we started with are planes. Were you aware of that? That when you say x plus y plus z equals 7, that's a plane. So what we have in the problem is 3 planes. So think of the front wall, the side wall, and the ceiling. 3 planes are coming together in a single point. That would be the corner of the room. This is the point that those 3 planes intersect. Now, out there in the random world, do you think it's possible to have 3 planes that don't intersect in a single point? Oh, absolutely. And that's going to happen to us, and we're going to talk about it. But for now, we have the best case scenario. They intersect in a single point. All right, get your calculators out. And let's do this using Gauss-Jordan reduction. We can also do it with Gaussian elimination, but then it still takes this extra work. So we're just going to do Gauss-Jordan on our calculator. All right, so second matrix, let's put it in. Edit. How big is the matrix we put in? 3 by 4. Let's put in our numbers, put in the original numbers. Oops. And then second quit, always in this menu. All right, now, everybody got it in? Okay, so we'll go back into second matrix and we're going over to math. Now, scroll down and you will eventually run into REF, which stands for row echelon form, and then RREF, which stands for reduced. So pick that one, RREF. Then second matrix, enter, that's A. So now your screen says RREFA. Press enter again. And the matrix that came up is in reduced row echelon form, but doesn't it give us exactly the same answers that we got? It says x is 2, y is -1, and z is 3.
Can you like redo what to press on the calculator? I missed.
Do you have them all in?
Yeah.
Okay, second matrix, math, RREF, all the way down to RREF, enter, second matrix, enter, enter. Okay, now the beauty of that on the calculator is we could have pressed the REF button and it would have given us this matrix, but then we would have still had to do this substitution. So pressing the other button just saves us all that time and we just pop up the answer. Okay, all right, let's try another one. Here we go, by hand. I don't care if you want to type it in and know what the answer is ahead of time, but we have to know this process by hand. On test day, you will do one by hand, or quiz day, or sometime. You're gonna have to do one by hand. So let's go through it again, very carefully, making sure we know what's going on. All right, so step one, write down our matrix. And then I'm gonna do a quick double check and make sure that I copy it right. So I'm gonna do that. Okay. When we're doing matrix operations, we usually use arrows instead of equal signs because, to show the flow of our work. The directional flow of our work. Okay. All right, so who knows how to start? Aiden?
Multiply the top row by -2.
Okay. First of all, I'm gonna write down the top row. And then, Aiden, you're exactly right. I am going to use this number right here to get rid of this number. So you said times by -2. So BRB, I'm multiplying the top row by -2. The top row by -2. Now I'm gonna add it to the second row. So I'm gonna get 0, 3, -5, and 6. Does that look okay to everybody? Now it's not as awesome as last time, because that's not a 1, but that's okay. That's all right, we'll deal with that. Okay, now what? Add the top and bottom. They're set up to eliminate, so we'll just add them together. So I get 0, 1, -1, and 4. Could I switch these two so I have a 1 there where I need it? Sure, what the heck, let's switch them. So then I'll have the 1 right where I want it. Let me tell you what happens, if you don't switch it, eventually you're gonna have to make that number a 1, and you're gonna have to do it by division, and then you're gonna have fractions. So if it's possible to make it a 1 without getting the fraction thing going, let's do that. Is everybody okay with what we did there? There's really only one more step. What happens now? So I'm gonna recopy the top 2 rows because they are fine. They're perfect. What am I gonna multiply to get rid of this guy right here? Middle row by -3. I'll write it down here. The middle row by -3. So this is the middle row times -3. Now I'm gonna add those together, and there comes my 0, right where I wanted it. And I have a -2 and a -6. Oh shoot, I thought I was done. Have to squeeze one in here. So 1, negative 1, 2, negative 3 is my top row, 0, 1, negative 1, 4. And this row has got to be divided by a negative 2, because if you're using Gaussian elimination, your last matrix has to be in echelon form. Right? And now it is. So now I'm ready to produce my answer. It is fun. What's the bottom row say? Z equals 3. And then back up, go to the second row now, the middle row. Y minus Z equals 4. So Y minus 3 equals 4, so I guess Y is 7. And then X minus Y plus 2Z equals negative 3. So X minus 7 plus 6. You get negative 2. So our answer is negative 2, 7, 3. David?
How did you go from the last step? Like you said you divided it by like 2 or
Negative
something?
2.
Wow.
That has to be a 1.
Oh, so you can just do that?
This is an equation. So if I said negative 2z equals negative 6, aren't I allowed to divide that by negative 2, David?
Yeah.
Yep. Remember, the rows just represent equations. Okay, we gotta do one more. Come on. Stop it, hang in there, we gotta do one more. All right, so here we go. Stop it, you're getting the hang of this, it's easy, it's quick, you got it.
Opposite of quick.
Instant world of technology. All right, here we go, let's see if we can get this going. You don't get to have class tomorrow, so we need to pack it in. All right, this has got some not so nice numbers in it. Okay, so you know what to do. You know that you're gonna recopy the top row, because it's perfect as it is. And, oh, this is easy. Right? So we'll just add these two together. So 0, negative 1, negative 4, and 7. This one we're going to have to work for. So we'll multiply the top row by negative 5. So that will give us negative 5, 15, negative 5, and negative 20. So 0, 2, 8, and negative 12. Double check my work, is that right? And now I know that's a negative 1. I can fix that easily enough. Now my top 2 rows are fine. I'm gonna write that middle one as 0, 1, 4, negative 7. Is that okay with everybody? Just dividing it by negative 1.
You just divide that bottom one by 2.
Oh, I could. I absolutely could. So Lane, what Lane's saying is, I gotta somehow make this a 0. So Lane says, what if instead of multiplying, I took this row and divided everything by 2? Now that's kind of tricky. That's not normal procedure, but it's absolutely okay. And we can add them together then, we get our 0, 0, wait. Is that what happened? Okay, why is this bothering me? Exactly. The bottom row literally says 0z equals 1. That is not possible. So what does that mean about these three planes that we started with? They don't intersect. They don't intersect. Remember when we did regular elimination? We would get something like 0 equals 8. This is the same thing. It's an impossible situation. So there's no intersection. Aren't you glad we did that?
Yeah.
End on a high note.